Welcome everybody to klogW. This is the first of 3 special talks for our newest APS fellows elected by Gsnp to fellowship. So we will begin with Jean Carlson today, go on to Denis Bartolo on January 19th of next year, and Yamir Moreno on February 22nd of next year. And over to Daphne to tell us a little bit more about both the series and GSNP and Zoom etiquette. And then John, the third member of our committee, will introduce Jean.
Hi, everyone. Welcome to the November klogW series. As Shubha said already, we're celebrating our APS Fellows nominated by GSMP. Today's speaker is Jean Carlson from Santa Barbara, who's going to start her talk in a moment. But yeah, we also have Denis Bartolo and Yamir Moreno coming up January and February. So please join our mailing list if you haven't already. But also, what I would like to encourage you to do is to join GSMP. You can do it through our American Physical Society Engage webpage. If you're not a member of APS, please join that too. And then join GSMP. The more members we have, the more prizes we can have, like the ones that we're going to hear about today and the following sessions. Awards for students as well as faculty, focus sessions at March meeting, and also events, networking events, professional events, and so on. So this means more statistical physics and nonlinear physics for everybody. This is what the Engage website looks like. So you can join GSMP by pressing here, and please go ahead and do that. Now, for today's talk, here's our Zoom etiquette. So during the talk, please make sure you're on mute. This is the first thing to do right now. Feel free to post questions in the chat box for the speaker. If they are clarification questions during the talk, one of the members of the committee will interrupt Jean and ask her the question. But otherwise, we will save them for the end. And if there are too many questions, we might save them for the end. After the talk, you're free to raise your hand and unmute yourself and ask the question directly. So that's a more sort of lively seminar-like conversation. If you have issues with your mic or you prefer not to ask the question, not to unmute, you can post your question in the chat box and we will call your name, but if you can't, that's fine. We will ask the question nonetheless. So this is it from me, and I'm passing it on to John to introduce Professor Jean Carlson.
Thank you. So it's a great pleasure to introduce Jean Carlson. So Jean got her PhD at Cornell, studying glassy systems, biophysics, and other complexities, and then moved to UCSB as a UC Santa Barbara, California, Santa Barbara, as a postdoc studying earthquakes, and has since stayed then and really has become known, I think, for a variety of very creative approaches to the study of complex systems with applications in immunology and ecology, fires, materials failures, disaster responses. One part of her work that made a big impression on me was the work in collaboration with the engineer John Doyle, a control theorist, on highly organized tolerance. And I think that'll make an appearance today. As Shubha mentioned, Jean is one of our currently elected APS fellows, elected through the GSNP, and she'll be recognized officially at the March meeting in Chicago in a few months. But for today, we get to have her for ourselves. So over to you, Jean. Thanks.
Thank you very much. I'm going to share my screen now. So I really appreciate the honor from GNSP. I was actually long ago, I was a secretary treasurer for the group. This is, dates way back and long before there were all these other groups. So it was really a leader in terms of getting physics out there into applications, broader applications. So my group, as John mentioned, has worked on all kinds of different topics. So we emphasize ideas that have to do with robustness trade-offs, multi-scale modeling across a lot of different applications. So today I'm going to talk about, let me get to that's okay, forest fires. And forest fires bring up decision-making, impact of forest fires on humans, decision-making in areas such as evacuation and resource allocation. And once you start thinking about that, you realize, oh, well, current times, yeah, first of all, you have to communicate over the internet, social networks. Current days, we're dealing with cascading disasters. What do we do if we have a forest fire in the midst of a pandemic? And then what about climate change and disturbance ecology? How are our systems recovering? So my intent here is just to say that basically all these things are intertwined and intermingled. And I want to talk today about fires, but really the fires stretch across a range of applications when you start to look at the impact of fires, and require a range of different kinds of tools. And really what ties it all together is looking at trade-offs, dynamics, and robustness and fragility. So again, today is fires. For my own personal history and thinking about this problem, it dates back to the late, around the turn of the century, basically, when there was a lot of interest in the physics community about power laws and critical phenomena and high variability. There was a lot of, at the time, people were thinking about critical phenomena in the physics community. And so my tack with John Doyle, as John had mentioned, was to say, how do people in engineering or biology think about power laws and trade-offs? And we came up with this idea of highly optimized tolerance. So I'll start by telling you a little bit about that. And in my group, this really led both to the development of kind of simple illustrative models based on wildfire-like mechanisms, but then also collaborations with people that were really in pyrogeography, right? People who did higher fidelity fire modeling. And we developed a highly optimized tolerance inspired fire spread model called HFire, which turned out to be computationally much more, thousands of times faster than what the Forest Service was using at the time, which allowed us to take these kinds of modeling tools, not just into short individual fire simulations, but towards long-term simulations. And then we use these kinds of models and fire models to start to look at trade-offs and scenario studies relevant to human interaction with fire, so in the built environment. So we looked at things like resource allocations across multiple fire events, dynamics and timing of suppression actions, and evacuation decision makings in populations. And most recently, I've been working in with the Risk Institute, the Garrick Institute for Risk Studies at UCLA, National Hazards Research Center, and looking at a variety of broad community-based impacts and global sort of multi-system kinds of modeling challenges that have to do with fire. So one of the things I'll tell you a little bit about is public safety power shutoffs, but also there's a lot of interest in medical, in community impacts. How is the changing climate and the ocean and atmospheric effects impacting fire, and what are the feedbacks involved in that? So hoping to go all the way around the circle today, but I want to at least let you know that really, fire is just a piece of a larger puzzle, and that a lot of the opportunities now come in trying to take a multi-systems approach. In a lot of these cases, while there may be a very high fidelity model of one thing on one side and one thing on the other side, there's very little work done to really understand in detail what the trade-offs are associated with linking these phenomena. Okay, so I'm going back to the beginning, and this interest in power laws that swept through the physics community back in the sort of turn of the century. This was not a way that people in the fire community or earthquakes community really were thinking about plotting their data at the time, but the physicists were very interested in it because of the history with critical phenomena. And so they started looking at power laws all over the place. And here is just some data for power outages and technological losses and natural disasters. And basically the idea is you plot on a log-log scale, how often, what is the rate or frequency as a function of the size measured in some measure, which need not be physical size. And you get some kind of power law signatured by some, linear slope. So here for these data sets, it's about a -1. The bigger message, rather than just the power laws, is really that while most of the events, the median event, the typical event is small, most of the losses are associated with the few largest events. And that this is completely consistent with the statistical distribution. Large events go along with mostly small events. They are not unexpected, and they aren't even always a bad thing, but you need to keep them in mind when it comes to things like suppression or any kind of action you might take. If you run and go and try to throw your suppression resources, say, to all the small events, you might not have anything left for the large events in the end. Okay, so this idea of highly optimized tolerance then is something that we call HOT, and it's a mechanism for complexity that's based on ideas from engineering and biology. So it's not coming from critical phase transitions, but we'll use a language of physics and percolation in order to illustrate the phenomena. And the idea is that you've got some kind of a constrained optimization problem. And if you're going to suppress the, the instabilities or the fragilities to known or known uncertainties or known perturbations, then you have, because of the constraints, some pop up to some new fragilities to unknown or rare perturbations. So it's basically like a waterbed effect, where you have certain kinds of constraints or resources that you can allocate, and that allocation will make you robust to the designed for uncertainties, but you're left with fragilities elsewhere for later on. Okay, so the question is, does this apply to forest fires? Okay, are forest fires hot? Well, in one sense, yes, of course they are hot, but what about highly optimized tolerance? Okay, so if you think about real fires, what's important, right? Well, in a real fire, you're interested in the intensity of the fire, the frequency, how large it is, how costly it is, how many people are affected. There's an ignition source that would be sparks, it might be lightning, it might be human. There's weather that feeds in, the wind conditions, the humidity. The topography, how, is it hilly, what type of soil, where are you in the season in terms of soil moisture, and then there's the actual trees and shrubbery that would be involved in the burn. So if you're talking about true forest fires and you want to model the phenomena, you really have to take into account all these phenomena. But I'm going to start with the real abstraction of the problem, where what we're going to think about is just a burned region in a sort of two-dimensional landscape, and look at an allocation of resources where the fire suppression mechanism must stop at some perimeter for something that's burning out radially. So the idea is an optimal strategy maximizes the yield of the forest, like a managed forest, while trading off the resources and the risk. So the language of this was something that really grew out of what people were calling the forest fire model back in statistical physics at the time. So Per Bach and a lot of other people were very interested in this idea of self-organized criticality. And so they talked about this sort of dynamics in terms of a forest fire-like phenomena. And this work with John Doyle, who's an engineer at Caltech, we basically tried to take that language and talk instead about this hot mechanism using a similar type of language. Okay, so the idea is you start off just like square site percolation on a square lattice, and you occupy sites. So here I'm showing just occupying sites at random. And then the idea is some of these clusters are connected. So we'll say adjacent sites form a connected cluster, and some of them are singletons and some of them aren't occupied at all. And then you have a spark that comes and it hits the site on the lattice. And a spark that hits an empty site does nothing, but a spark that hits an occupied site will burn through and cause a loss of that cluster. So it's basically like a fuel limited fire spread that will only spread, that will spread fully throughout a cell that's occupied and stop at a vacancy. And so the optimization problem then becomes optimization of yield in the forest after, say, one spark. So the idea is the yield is the density I would have to begin with minus the loss due to the spark. And so if I just look at this and I imagine I have a single control parameter, which is the density, and there are no sparks, then the yield is just equal to the density and it's a straight line. But as soon as I introduce a spark, then, and a random spark, say, then if I have a high occupancy in my lattice, I'm pretty likely to hit the large connected cluster and cause a strong drop in yield. So at very, basically there's a point somewhere in the middle that's the optimal point, which would be the critical point. And this would be the sort of standard physics story. And it sharpens up in the thermodynamic limit, and it's exactly that critical point of site percolation on a square lattice. So at very low densities, you have very sparse, few clusters, a lot of singletons and a couple of small, slightly larger clusters, but none of them are scaling with the system size. So the low densities fires don't matter, call it cold, right? And then at high densities, you've got a very large connected cluster and you're pretty likely to hit it. So everything burns. And then somewhere right in the middle, you have this critical point where your connected cluster is just finely system spanning but it's fractal, so it's not volume consuming. And so that's the sweet spot of critical phase transitions. However, it's really not that dense, right? It causes the large connected cluster fire as fractal. It's not really burning a volume of trees. So is that really what fires are all about? So what we would claim is that really forest fires burn densely through, large patches of the forest, which is what we see. And so how do we make that, how do we understand that in terms of this type of model? So the idea would be, what about high yield configurations? Okay, so in these configurations, the barriers are much more organized. They're much more like, if you're cutting a fire break, you don't cut it as a fractal, you cut it as a sharp line because that's so much more efficient. And so these high yield configurations, they'll generate much higher yield. You won't have much loss if you know where the sparks are most likely to land. And so that's really the question. So these high yield configurations are not what you would get if you randomly threw trees out on the landscape. They're structured, they're mostly ignored in traditional physics, but yet this type of thing where you've designed your system, or your system is organized or evolved or ecologically, sort of self-sustaining, are the kinds of things that are much more ubiquitous in engineering and biology and ecology. They're not random, they've got structure. Okay, so this was really what Doyle and I set off to study. And what we found was that almost any distribution of sparks, if you optimize the yield, you would get these power law distributions of events. And we looked at a lot of different models and analytic and numerical results. And so I'll just show you a little bit of how that goes. So here's the idea. So I'd have some kind of a two-dimensional, again, landscape. There might be a region with high probability of sparks, tops of mountains, near roadsides, regions of low probability. And I could say, where would I put cuts? So this is an analytic problem. You can say, where would I optimally position cuts in this two-dimensional landscape? And basically, these are my fire breaks. And so you generate a configuration, you can compute the global optimal, and it gives you small events. You basically concentrate the cuts in the regions of high probability. So small events are likely, and you leave open the possibility of of a large event, but they're very unlikely because they're in the region of very low probability. And this optimization problem yields very high yield. So on the same graph as the percolation-like problem, I can get to very high densities, again, under the same kind of scenario if I have, I have one spark drawn from a distribution. Okay, another way you can see this is to grow your forest one site at a time, each time adding a tree or occupied site to a location that gives you the highest yield. So you start off filling the corner, which is low probability, and you keep adding density. And so here I am later on where I've got 80% density and 80% yield because I'm just so unlikely, I'm so likely to hit up here in the corner. And if I happen to hit somewhere out here, I'm only losing one tree. And then over here, I'm very unlikely to hit. So I basically could grow and keep growing and adding until I finally get to an optimal situation where now I'm going to have to start filling these higher probability sites, and then there's a crash. So this is just, the red curve is showing the trajectory of the growing one site at a time, up in density until finally you get a crash. But again, just like the cuts model, you're getting to very high yields with an organized forest. So both of these mechanisms produce power laws. So does critical phase transitions. It's much flatter. This is shown as a cumulative probability distribution. So these solutions, though, are, and they also produce macroscopic fires. So the critical fires, as the lattice size becomes the thermodynamic lattice, these become fractal, and so they're not actually volume filling. Okay, so all power laws. The thing that these sort of hot lattices do is they basically illustrate this idea of robust yet fragile. So what does that mean? That means that I put in some structure to make my system more robust to say, to be able to preserve high densities with smaller fires, but yet I now, because of those structures that I've added, I have introduced new fragilities, the water bed effect. So small flaws give me a, terrible disaster. If I can now hop my fire breaks, now I'm going to have much higher losses. So what was once a very high yield configuration becomes a very low yield configuration once I have cuts in my fire breaks. If the probability of the sparks change, if all of a sudden what was a very low probability, or not even all of a sudden, if eventually what was a low probability event becomes a higher probability event, that can also be a disaster because I've designed for low probability here and high probability up in the upper left corner. So the trade-offs that have been made is basically by introducing design, I reduced my sensitivity to sparks, but I've increased my sensitivity to assumptions about the distribution of sparks and to flaws in my design. Okay, so that was really how I got into thinking about fires. And I started talking to people in the geography department who had a wildfire center and started to really actually look at fires and interact with people, fire scientists. And so what do people really use fire models for? So one of the things is to predict fire spread patterns. They would just, here's a fire, and then now we want to see if we can simulate it on the landscape. So drawing on realistic data for the topography and the fuel types and that. So there's a model the Forest Service has used for years called FARSIGHT, which aims to do that. There's also physical models where you really include combustion and atmospheric effects, and those are very computationally intensive, but those are some of the kinds of things people use models for. They also can use them as a test bed for scenario studies for protecting people, like where should we put our fire breaks. You can use these as training for firefighters. So you can sort of basically have a fire simulator and a firefighter who's going around and practicing their suppression methods. You can use them to help quantify things that you don't have good measurements for. So there's a lot of issues there. You can set insurance rates based on modeled projections, develop protocols for policy and management, and predict long-term consequences of urbanization and climate change. Okay, so here's some fire facts. They're a few years old. We think of fires so much in California and the Pacific Northwest, but if you look at fires in other parts of the world, they're bigger and worse than some of the things that we've seen here. So some of our recent, very largest fires, California, have been kind of hitting 1 million acres, but there's, the largest, deadliest fire, at least at the time when I was putting this slide together, was 18 million acres and fatally injuring over 200 people. Australia had, in the 2019-20 season, they have a ton of fires there. It's grassy lands and they burn every year. And so they had 46 million acres of burning. In 2018, we had 8,000 some wildfires, 1.8 million acres, which is a lot. And there's really a lot of properties in California at risk for wildfires. There's a lot of development in the wildland-urban interface. And Texas is second in the US in terms of properties at risk. And then the other thing is up to 85% of wildfires in some way is caused by humans through unintended campfires, cigarettes, equipment use, public safety, or just power ignitions and so on. So these are statistics. So one of the things that we have done, so basically for the last 20 years, has been working with the members of the Southern California Wildfire Hazard Center at UCSB. So this is a group in geography that develops models and does a lot of satellite measurements and fuel studies to develop models for wildfires. This is Dar Roberts, Marco Marias was the student working on this, and Max Moritz, who's here now, and is a fire expert in geography and in the Bren School for Environmental Science, Policy and Management. And so the idea was to basically take some of these ideas and to look and develop, rethink fire modeling. And then these models have since been used for looking at problems involving resource allocation and fire suppression. And the other thing that we've done, because we've had an interest in neuroscience, is to look at human factors in evacuation decision-making. The geography department also has a lot of people who work on traffic models, but there's also just a question of what actually is, what are the bottlenecks when it comes to evacuation. Okay, so now once you start to measure real fires or model real fires, you've got to come back and start thinking about what are the hazard factors. So the terrain, the slopes, the facings, the roads, the rivers, the fuel conditions, how old are they, how dry are they alive or dead? And then the weather is a huge factor. So in Santa Barbara, we have these sundowner winds, and there's the Santa Ana winds and Diablo winds up in the north. And these are all just heavy winds that are driven from basically the backcountry towards the shore, and they can reach 80 miles an hour. I mean, they're really, really high wind conditions. And when you have a high wind like that, there's kind of nothing you can do when it comes to fire. Okay, so what was the advance for this idea of fire modeling? Well, used to be these Farsight and the models that the Forest Service were using. They used this model called the Rothermel equation. It did build in all these features from databases, but they had a way of evolving this forward, which was very inefficient computationally. And so Marco took this idea of the sort of percolation-like model and developed a raster spread model for fire spread. And so it basically, each cell has features that determine the direction of fire spread, but you just sort of think of it not just now as an all or nothing of it's either occupied, vacant, or burned. You now have features like the slope and the fuel on the model, and you basically can consume that fuel at a rate, and fire will propagate at a rate that is dependent on the wind. So we took as a study area Santa Monica Mountains. It was easy to simulate. There are all kinds of different fuel types. And we also built in successional fuels. So if you did burn, then you would regrow at a certain rate through a succession model. Okay, so it turned out that this was way, way, way more computationally efficient than Farsight, but yet produced very similar results to the algorithm that the Forest Service was using. So we compared, basically validated the model in comparison to the data and also to Farsight. The data isn't actually as high resolution as this. So this is hour by hour progression. And part of the problem is that especially at the time, the satellite imaging and heat maps weren't as good. And so you wouldn't have hourly updates. There was too much smoke to be able to even see in detail what was going on. But you could see where it progressed and what the perimeter was at certain intervals. And it was in agreement with that, and also agreement with this high fidelity, very accepted model that the Forest Service had. And this is just, first 34 hours simulated during and it occurred during a Santa Ana wind condition, and it was in agreement with what was seen. But the thing that was also really nice about this is that same resolution, because we had a much more efficient model, we were able to look at years and years of progression. So we would have a fire, and then it would be burned, and then you would regrow. And so you'd follow the succession pattern and be able to look at long-term effects. So this was long-term effects with kind of static atmospheric conditions. I think one of the really interesting challenges now is to look at how this sort of long-term conditions or repeated fires really can interact with the changing climate. That's one of the things that I'll mention later as a challenge that nobody is really doing right now. But there is the capability to look at long-term fire regimes. And one of the things we also see is that we get these kinds of quilts. The footprints of the fires are similar to what is seen in the actual data. This is a 5-year period. This is like 100-year period, and these are just showing some of the fires and how they overlap in space in our simulated run. And then the statistics look very much like the statistics that you see for Santa Monica Mountains or any of the other forests you might look at in California. So that's just a little bit about kind of what the history of this modeling was for me. We started with this very simple model, and we collaborated to develop this H-fire model, which produces this sort of patchwork fabric of fires that are seen in Santa Monica. This is our patchwork pattern of fires in Santa Barbara. So this has all kind of happened. This is an old one, but it all was happening at the same time when I was working on this model. And then the statistical distribution of fire sizes was, from the very simple model, was in good agreement with these models, as well as data taken from the Los Padres National Forest, which had a really good long catalog. So again, it's, with the combination of abstract models, detailed realistic simulations, statistical analysis. Now the question is, what do we do with this? And so what we've done since this work was really to move towards using these models to study proactive measures, resource allocation, evacuations. And then there's a lot of work and opportunity for new work on really modeling fire spread at the wildland-urban interface, impacts on human health, and how does climate change feed into this, both in terms of the condition of the environment, the atmospheric changes, temperature changes, rainfall changes, and then the feedback of fire, of course, with emissions and the changing topography that is caused by fire, or not topography, the changing fuel landscape that is caused by fire. Okay, so I'm now going to move forward. So what makes a wildfire a disaster? So I think this is a really interesting question. I had sort of recently, I've been working with a group through this risk center, and it says, why is a wildfire disaster, right? Really, wildfires are beneficial for many ecosystem types. We need fire for many types of seeds to basically germinate. It's a natural part of the process. It's not a disaster in its own right. It's it's a needed part of the dynamics in terrestrial ecosystems. So what makes it a disaster? So first of all, I think we're clearly seeing a new kind of fire in recent years. And I think it's agreed that fire suppression policies have contributed to these mega fires that we are experiencing now. Mega fires, both in terms of the size, the area, but also in terms of their emissions. It's just a whole new world. A part of this is climate, but part of it is just the condition of the forest and the suppression policies. It's not all about the size of the fire either. It's about really, when you look at what makes it a disaster, it's the loss of lives, loss of structure, maybe the impact on the ecosystem. But right now, in terms of firefighting policy, it's really, we measure these fires in terms of the lives and the structures as much as the size. And we have this understanding that the wildlands do need to burn. So there's a new focus on mitigation in the built environment, development of fire resilient communities. And this approach to wildfires, really, wildfire lags the science and engineering policy for other kinds of disasters. So if you think of earthquakes and hurricanes, where suppression would not be considered a viable option, there's an earthquake engineering. First of all, nobody thinks about stopping the earthquake in its tracks or stopping the hurricane in its track. Our approach is to make our societies more resilient. We know that earthquake's coming, and so there are building codes for bridges and buildings in earthquake-prone areas to try to make them more resilient. And this approach to wildfires is way behind compared to other types of natural disasters. And I think it's in part because our approach was, a policy approach was suppression. And so we just said, oh, we could just go put it out. And that has not even been an option for these other kinds of disasters, but it's a way of thinking and an approach to wildfires that basically sets priorities in different directions. California did institute wildfire building codes back in 2007. It was the first state to do anything like that. And our recent large fires have shown that these are actually effective. So there's not enough data to really, sort of lock this in. They're relatively new, but it's something where we should be thinking in this direction. And so one of the things that I'm going to point to as opportunities really has to do with thinking about the spread of fire, not just in the wildlands, which has been the approach of all these fire models, but really how does the fire spread into urban environments, and what might we do short of just suppressing the whole fire, but do things that might mitigate the impact on populations and structures. Okay,
Jean,
so
could I ask you a quick question about fire suppression? So
yeah.
does that mean just expecting to put out the fires if they occur, or is it more than that? Has it included like forest management and so on? Or when you say fire suppression, it's really just wait for the fire to happen and then try and put it out?
So historically, it was like people would just go. There'd be a fire, people would go try to put it out, and there was some cutting of fire breaks, right? People would talk about thinning forests, but if you look at the expensive, how much money is spent on forest management and suppression, it was 98% is on the reactive side. Very little is spent on the proactive side. So it's not that people weren't ever doing any thinning of the forest, but it was minimal compared to probably what should have been getting done. Is that helpful?
Yeah, thank you.
So that's the kind of question, right? And that's also a place where you can use models, is to talk about how might we prepare these forests in a way that would reduce the risk to populations. So that's exactly one of the important questions. So in any case, we've got the physical phenomenon, which is a fire. We've got mitigation and response, which could be suppression. And more recently, there's a greater emphasis on forest management. There's communicating about the fire and public policy. And then there's, human decisions when it comes to things like evacuation. Okay, so for us, one of the things that we did early on was to look at just resource allocation. So this idea of suppression. And we used two studies that are older, right? That were two of the, at the time, these were data sets that were collected by the Forest Service and CAL FIRE for what they called a fire siege in 2003, and then another one in 2007, where they had multiple fires. And then you're trying to figure out where to send your firefighting resources. So the factors that come in are, the size of the fire, how close are they to populations, what are the weather conditions at these different places. But at the time, these were major things, and now it's the norm. I mean, it's really become the norm. But at the time, these were useful to us, and we looked at basically like part of the issue is that when you delay, your fire grows. So you have to send more resources the longer you wait. On the other hand, you're taking resources away from a fire in order to do so if you've got a resource constraint. So, and again, time dynamics are vital for fire response decisions. This is something that wasn't being done at the time. They would just say, here's a fire. It's a certain size, but there was no growth of the fire in the lack of resource allocation. So I think there's some really important trade-offs involving time dynamics in fire and response that really, you don't have to have the highest fidelity model in the world to look at these kinds of problems. It's not specific even to fire, because disease epidemics, oil spills, other kinds of disasters have similar types of trade-offs involving response and dynamics of growth versus suppression. And so this is one kind of optimization problem that is very fundamental and relevant to the question of wildfire response. There's also these questions having to do with proactive measures. So there's, what are the actions that affect wildfire? There's, reducing ignition likelihood, anything you might do directly to sort of mitigate the fire, climate, anything you might do to try to reduce climate hazard, things that you might do to rehabilitate or prepare the landscape. And then when you have a wildfire, you have the fire, you have the smoke, you have post-wildfire debris flows, flooding, pollution, things like that. Water pollution has become a big thing. And then the actions that affect the outcomes. Hardening means, basically you might do things to make your system more robust directly, like, revamping your power lines and things like that. And then there's also things that you can do to reduce exposure. So build different places, things like that. So in any case, there's lots of opportunities here to look at trade-offs in these different areas and constrained optimization problems to try to figure out what to do. And so, for instance, if I look at a forest, right, here's a forest, and this is just basically a kind of sketch of what the forest looks like these days, right? Because we've suppressed fire, we've got like overgrowth, and there's a lot of shrubs and often woody materials down at the base, which makes it much easier for fire to propagate up into the crown and then lead to much more disastrous outcomes. This is what we're seeing now. And so this idea of thinning the forest so that you have not so much low growth, but it's a sort of cleaner base. This is something that Native Americans were doing and was much more what forests looked like before, say the last 100 years. Then what happens is you'll have burn propagating at the base ground fires, and you won't have, you know, the sort of mega fires that we're seeing here. So I think this is an opportunity for modeling to look at how different suppression policies, or not suppression policies, how different proactive, basically forest management policies could impact, you know, the health of the forest in the future. So again, there's thinning, controlled burns. This is something very much in the thinking now of the Forest Service, but I think modeling and deciding what needs to be done when and what its impact will be on fires in the future is an open area for work. Here's another thing, is what do you do about replanting? Traditionally, there were pines and lines, putting trees in regular grid patterns. Modern approach increasingly involves clumping the forest and trying to create an age distribution of the fuels within the forest. So this is like a heterogeneous fire spread problem, or and looking at what the outcomes could be. So how does that kind of heterogeneity in the forest, in terms of age, in terms of spatial arrangement, impact fires in the future? Another type of proactive measure really has to do with preparation of, you know, of the homes, right, of the built environment. So we see pictures like this all the time where you have a house and you really need to leave defensible space. So you're supposed to not have lots of vegetation close to the house, and you should clean out your chimney and roof and gutters, and you should not have ways for embers to get into the rafters of your house. So there's how do you create these are all part of the kinds of building codes to make new buildings more fire resilient. So one of the things that we're seeing more and more, though, in the recent fires is this impingement of the wildfires into the urban communities. So this is pictures from Oregon, where you can see here's before, here's after. The fire spread from here, and then it sort of got into the urban community, and it's just devastating. Right, here's some other pictures from Oregon where before, after, you have this huge amount of burn. So there's a lot of interest and not a lot of modeling when it comes to fire spread into the urban environment. Like how should we think about the fuels? How should we think about the ignition of a house? How should we think about that? So here's some work at NIST. There's basically vegetation spread, so the fire approaching the community. There's vegetation into a structure, and then there's structure to structure. So coming up with ways to really model the fire spread into urban environments is really an open question. And I think on the one hand, one can do very high fidelity modeling, but I think there's a lot of opportunity for sort of simplified models, which you can really focus on the trade-offs. So the trade-offs between, you know, what are the advantages and sort of different spacings of houses or different house preparations, things like that. So I found something. So I went around with some of these things that I thought were interesting questions. I went and looked, you know, are there people that are doing this now? And I found an example in Scientific Reports of somebody that was really trying to look at this, again, kind of from a complexity statistical physics point of view, where they had fire spread as a one-dimensional, or, you know, basically a front impinging on a community, throwing these spots. So it's basically burning embers. It's a spot, is what they call it, spot fire, into urban environments, and then it will hit a house. And actually, it doesn't necessarily even start the house on fire right away. It can be an hour later. It can be in the attic, and then it will spread among the community. So I think really looking at how these spot fires are thrown ahead of a burning front into a community, and how that changes how you can impact basically the resilience of the community by taking into account things like the layout, defensible space, ways you can protect your home, and then getting people to do it. Okay. Another problem that I've been thinking about lately is ignitions, right? And power power, electrical power. So this is from the LA Times, and it says, let's face it, preventing and fighting wildfires means utility customers will have to pay more, and we're seeing that already. So here's, California, and these are the transmission lines for the major utility companies, Pacific Gas and Electric, Southern California Edison, some other ones. And then this is one of these wildfire risk maps, right, where it shows the regions, by color, which are thought to be the highest risk to wildfire. And so clearly these are like overlaying each other. And so the question is, as we've had some of our major fires, like the Paradise Fire, be squarely, the responsibility squarely placed on the power company. These power companies are becoming, bankrupt or having lots of problems. And so can we look at how to make this safer, right? So basically think about the power grid, ignitions, proactive measures, whether it be hardening the grid or whether it be public safety power shutoffs. So people hate public safety power shutoffs when they happen to them, but the power companies, they want to do it if they think there's a risk of a major wildfire, because they don't want to have the liability for igniting a wildfire when you've got one of these 80-mile-an-hour winds and a tree falls on the line. So the power companies have started to develop, PG&E was bankrupt, and after the Paradise Fire, and all of the power companies have in place protocols that are for now public safety power shutoffs. And the first time this was really widely enacted was in 2019. So this is a pretty new process. And so the idea is you're sort of watching the fire, you're watching the weather. They have sophisticated models of the weather, even just the wind conditions that are predicted. They're watching fires come. They've got a kind of war room with large major computing. They're looking at maps and deciding which lines they might want to turn off, and then they turn it on again later. And sometimes it's actually the turning it on that causes the ignition. So this whole process is something that is very much development at PG&E and Southern California Edison, and they've got sophisticated networks. They've got people going out in the field and looking at where the trees are and how dry the vegetation is. They're using supercomputers to do sophisticated weather models. They've got very large databases of outages and outage causes. And then they have indices that are basically, sort of looking broadly as, like, is this a time of year and a location? So it's like a map for the fire potential in a region. Surprisingly, so I've been involved in kind of helping them assess their methodologies. I was also on a thesis committee for a student who wanted to do this, right? Was trying to take the data from PG&E and do some modeling. And it was surprising how little modeling has been done in this area. I mean, really, even analyzing the data, there hasn't been a lot of sort of what would be considered not PG&E internal work, but really, how could we think about this as like an optimization problem? So I think this is a really interesting example of a kind of coupled spatial physical problem and network model where you have an optimization where you want to preserve, electric power, for the most part, but you want to make sure you've turned it off if you've got a region of very high risk. And then how do you make that decision? So I think there's data out there that's being put out by the power companies. There's risk maps. It ought to be a more dynamic problem. This sort of color scheme is basically saying these are static risks. And this is an opportunity right now, is to really think about how do we build a sort of multi-level model between both the sort of fire risk and the distribution of power. Okay, and there's many other co-evolving network challenges that require advances in statistical and nonlinear physics, dynamical systems, understanding human factors in order to basically try to figure out where where the tipping points are in these decision problems. And they involve trade-offs. You've got to do one thing or the other. And decisions that you put in place may cause your system to be more fragile as well. Okay, so I am looking at the time and I can see that it's getting close to 10. So I think what I'm going to do is I'm going to skip forward, and I'm going to quickly stop, and I'm going to move past some of the things that we've done on evacuations. So one of the things that's been a big part of my group's work in recent years has been on human factors and decision making, and that's its own story. There's also really interesting stories in terms of thinking about human health and smoke produced by fire, but I'm going to just switch here to the end and kind of talk a little bit about just how should we be looking at fires. So this is showing a fire and in Sierra National Forest, and it's showing the air quality index as a function of time during the fire. And, you know, basically size, you've got structures, you've got suppression costs, you've got fatalities, you've got populations affected by unhealthy air, and then you've got the potential for permanent loss of forest. So there's really multidimensional problem here that we need to think about when we think about fires. It's not just about fire size, it's all these different things enter into the costs. And then there's really the question about things getting worse. So climate change, it's not just a static statistics of what the environmental conditions are, atmospheric conditions are, these are changing. And if we look at just in California, the top fires, for me, December 2017 was a horrible year. It was the Thomas fire, and that was an electrical ignition. It was the largest fire in the state of California at the time. It affected, you know, it spanned from basically Ventura all the way to Montecito. And yet look at all the fires that are larger since then, right? In 2020, 2018, 2020, 2021, we're already down to 8. So the largest fires, they're just getting larger. And this is just some pictures. Here's, you know, like Ventura and Ojai, and here's, you know, Montecito, and we can see it's a giant fire. It looked like this all the time. This is Santa Barbara, and you just couldn't even breathe. And so, furthermore, even before the fire ended, there was heavy rain that gave rise to debris flow and flooding, covered the 101 highway, loss of life, injuries, breakdown of transportation. And it's, again, before the fire was even officially out. This is happening in British Columbia this year. So they've had major fires followed by major flooding with atmospheric rivers. So things are getting worse. There's feedback from fire into climate change through emissions. And so costs are going up. And so we really need to think about how to make society more resilient, and how fire, not just fire, but fire and its interactions with the ecological and the technological and human environment. So what makes wildfire disaster? We really need a systems-based approach to wildfire engineering that parallels earthquake engineering. The suppression policy has made fires worse, not better. And it mandates new strategies for forest management. It's not about size, it's about loss of lives, structures. Once we get that under control, we can really think about the ecological costs as well. But the risk functions are multidimensional, and we need to think about it that way. There's new focus on mitigation in the built environment, wildland-urban interface modeling, resilient construction, defensible space, communication and evacuation, getting people to to leave when they should, educating the community, impacts on healthcare. And so all together, this is basically saying we need to be thinking about networks that involve trade-offs and dynamics involving social, ecological, and technological systems. And climate change just makes this work more urgent. because of feedbacks involving emission, and that it's fire is a pathway in which the environment and ecosystems change. So I will stop here, and thank you very much for your attention.
Thank you, Jean.
Thank you, Jean.
I see a question in the chat, which is a two-part question, actually. Would the person like to ask it themselves? Unmute and
So can I ask, should I undo my slides and just make it people faces?
Sure.
Okay.
Hi, Jean. Thanks so much for your talk.
Hi.
That was wonderful. I have two questions that are unrelated to one another. The first one is about the culpability that you mentioned about the power company. I mean, since you're in such a high susceptible situation, anything could have started the fire. And I mean, it's very difficult to attribute culpability to one particular source because there's so many sources and it's just a random selection of what finally does the spark and blows the whole thing apart. So can you say something about that? The other thing is, I mean, is there a relationship between the hot theory and the hot model and explosive percolation? Because there you also have like a correlated buildup that forestalls the percolation threshold, if you like, and then leads to that powder cake that then suddenly explodes, just similar in your hot model there.
Yeah, so the first thing I would say is there are like forensics for fires. And so you can trace back origins to starting points. And so it's something where it can sit and be undetermined for a while, but it's sort of like, yeah, so that.
Sorry, that was actually not the point. Not that it can't be traced back, but is it meaningful to trace it back? That's more the question. Because not that, something else would have done it and it would have happened inevitably, like that Los Alamos fire. I mean, it was the fire service who tried to do a preventive burn, and that created...
exactly. Yeah. So that's the one that when I was first starting this work, that had just happened, and it was exactly that type of cause. I think that one of the things that's been true of the power companies is there is this notion that they have, we've pushed the grid. So that original statistics that I had for power outages had nothing to do with fire. It was just outages. And it was because the power grid really had been built for a certain level of, of power delivery. And it's just gotten pushed and pushed and pushed. The equipment's gotten older and older and older. And so you can see that some of it was not in good shape. And so there's this real rush now to go around and harden the equipment. So it's basically system hardening. They're replacing things that they weren't replacing. So I think that the lawsuits and all of this culpability measures really targeting the fact that there was equipment that should have been replaced that wasn't, and it was throwing a spark. So on the one hand, there's a huge culpability based on the fact that we've been suppressing the fires and we've set ourselves up for these large fires. And if it wasn't going to be, a power line, it was going to be a lightning strike. And there are a lot that are lightning strikes too, but I think there are some that are clearly power lines. And this culpability is really saying, okay, you really need to go out there, fix it. And I think what happened is with like the Paradise Fire, the one that sort of came down the mountain and swept through this community, Paradise, California, that was a power ignition. There was a lawsuit because of the equipment failure, and so then that really sent PG&E into, into bankruptcy because they were held culpable, and then and now they're trying to get out of it, via the California Public Utilities Commission. But it is complicated. We're seeing a lot of lightning strikes this year, and I certainly think the utilities are working really hard, which is good, to try to rectify this problem. Yeah, okay. And then in terms of percolation, so I think, it's interesting because there are things that you can start to think about, which would be like delaying the onset. You could also imagine you could imagine, sort of how would I design a system if I give myself certain design degrees of freedom? Like I could make it tune the density, not just like overall, but tune the density in subsets of the region in different ways. And I think we tried to look at that at one time and sort of imagine that there were design degrees of freedom in different cells. And what we found is that the system really wanted to be hot. It really wanted to be fully occupied without a lot of holes. And that solution was a better solution with perimeters that might be at lower density. But whether you really want to do it as randomly as percolation would tend to build this. So we've got, there's a variety of models we've tried to do to try to look at a bridge between hot and percolation. And we've always found that sort of the critical phenomena solution is just a corner, because once you allow for a system to grow at higher densities, it really wants to be space filling in those regions. So it's a longer answer than a 2-second one, but it is an interesting question. And I think more work that way, trying to bridge various kinds of models, is useful. And certainly things aren't grown solid either, right? So the real growth mechanism in ecology is one where seedlings land from trees. Either you deliberately are planting your forests, but more often than not, seedling lands from trees and sit at the base and repopulate the forest. And so that looks random. It's just a question of how compactly that builds the forest. So I think there's an organization, not necessarily an optimization, and the organization can be built through ecological mechanisms that may have elements of them that have a little bit of a flavor of random-like growth.
There's a question in the.
Oh, I was going to say that leads into a question by Rostam.
Okay.
Do you want to ask that?
Yeah. Okay. So here's another one. So when plants regrow after wildfire, does new vegetation that naturally begins to grow spatially spread out to avoid percolation of future wildfires that may immediately occur afterwards? So this is, first of all, this is a really good, interesting question. So part of the regrowing is, is giving seedlings a chance, right? So if it's a forest as opposed to shrublands, then you sort of have seeds that are in the ground, and they may not actually do that well because of large trees shading them. So you get a chance for all kinds of new things to grow that didn't grow before. And let's see, I don't think there's no avoidance of percolation of future wildfires. I think, in fact, one of the interesting things that has happened recently is that a lot of times the previous fire is a natural fire break to a fire that occurs later, right? That you'll have a fire here in Santa Barbara, like right up the hill from me, and then the next fire will burn, and then it will slow as it enters and die out when it enters a region that has built recently or burnt recently. So the fuels that are most flammable tend to be associated with older growth. And there's a kind of recurrence interval for fire in a healthy forest that might be 30 to 50 years for shrublands, and it might be 100, 200 years in older growth forests. And it's something where the amount of dead fuel and low moisture content is really what determines whether a large fire takes off. Now, that said, it's not unheard of to have fire spread into the same region that burned a year or two prior. This happened down in San Diego. It happens near roadsides too, because of cigarette butts and things like that. And that is one of the mechanisms that causes type conversion. So type conversion is where you go from having a particular vegetation to replacing that vegetation with something different. So for instance, by roadsides, you are replacing, something that might be more shrubland, like with grassy, flammable, high flashy types of fuels. So this is one of the things that gives rise to ecological change over time, and I think is accelerated by climate change, because we'll have more burn cycles and the burns will be more overlapping. And so then instead of getting, our nice chaparral back, instead now we start to have grasslands in certain regions. So I think there's a, there's that kind of mechanism. So there's all kinds of, I guess what I'm trying to answer is that there's a lot of interesting mechanisms on the regrowth side, and that having a little more interaction between the fire and the ecology side of the problem is also open for a lot of interesting modeling right now. Because I mean, there's sort of like, oh, there's part of the root structure is actually how the plant regenerates, and it only grows when there is a fire. It's dormant until then. That happens with some kinds of seed pods. So then it would replace with itself. But if it burns while it's young, then you've lost that plant. So I think that's a really interesting question.
Jean, a quick follow-up to that. I mean, there was a study in PNAS that I saw which said a lot of the fire that spread across the US, the responsibility lies with invasive species. So is that, old growth being replaced by invasive species, and is that human caused? So
that's very, human caused, either humans or it's like a, it's the stowaway on a on a boat that's come in for somewhere else. But yeah, so there's, for instance, in Santa Barbara, there are these eucalyptus trees that are non-native to our region, and they are beautiful. They're very tall and beautiful bark, and they go up like torches. So if you have a eucalyptus tree in your front yard and it catches fire, it's full of oil. So you can see it. It just goes, shooting up, and then it's terrible for you and terrible for your neighbors. And yet you put it there because you thought it was beautiful. And so invasive species can be big problems because they aren't fire adapted. I mean, the real ecological, story is one where the landscape is co-evolved with the fire regime of a region. And so if you look at what would be like a steady state, right? There's certain plants on the landscape that have evolved for the fire regime of Santa Barbara. And when climate change starts to happen, not just to Santa Barbara, but throughout the world, plants that were once adapted to the fire regime locally are now not anymore, because now we're getting more moisture, less moisture, all kinds of longer summers and shorter rainy periods, and that process is one that's going to change where the fire prone areas are going to be. And it may leave us with deserts in regions that were once nicely green. And it's not, the addition of basically invasive species only makes the problem bigger.
Craig, go ahead and ask your question.
Hello, hi everyone. Hi, Jean. That was a very nice
Craig.
talk. So I was wondering about the, in the earlier stuff with John Doyle on the hot and the fire breaks, there was really no dynamics for the events, right? You spark and the whole cluster goes all at once, right?
Yeah.
And then the H fire, it looked like there was temporal dynamics, and you saw the front propagation was really close to the more elaborate model. So I'm wondering if you could say something about how the dynamics, the time dependence comes into the H fire model. And then if you could relate that. So if you try to make an analogy with other front propagation stuff, like a domain wall that gets pinned on obstacles, you would imagine that you only see critical stuff happening when the field is close to the critical field, right? And so is there something in the forest fires, like the driving, I don't know, like the humidity or the temperature, the Santa Ana winds, that plays the role of determining how close the field is to the critical field or something like that?
Yeah, so this is a really good question, because you're right, that original HOP model just focused more on the static and the layout, but we've when you look at the more realistic fire model, or you can set the HOP model up to have this as well, because we've done that. There are these drivers of fire, right? There is the fuel, obviously, but there's also wind and topography. So wind is a huge driver. And when you have a Santa Ana wind, you will have the fire moving so fast you really can't do anything about it. So I think, speaking, if you have 100-mile-an-hour wind, you've got a 10-mile-an-hour fire front moving forward, and nobody's gonna be able to do anything about that. But then when the wind dies down, or you get some rain, cools off, then higher humidity, then you have a chance to stop the fire. So when we had first developed the H-fire model, nobody had put termination in those models. Those models were just fire spread, and the fire spread would depend on the wind and fuel conditions and the weather and all that. But we put in a threshold for the termination of the fire based on the rate of spread. So we said, okay, once the rate of spread falls below a threshold, then we'll say this has gone out.
It gets stuck. It gets pinned.
Yeah, it gets stuck. It gets stuck. So it's really, and then what the percolation model would be is it would be a purely fuel-driven fire. It wouldn't care about wind conditions. And so it turns out that really, that wind condition is critical to understanding. And it's not necessarily, I guess there are places where you just have large old growth forests and it's not as wind driven, it's more humidity driven, and you're just waiting for the rain to come to be able to do anything about it. So you can go, and the more resources you give the fire, you could put a cost function, like what firefighting resource would I have to allocate if I wanted to stop a fire that's spreading in such and such a speed? And the Forest Service has that. There's a whole table, this takes airplanes, this takes, fire trucks, this takes, some other thing. So there is a knowledge of what can be done by what.
And then, so I guess the question would be then the good agreement between the H fire and the more elaborate thing, how dependent is that on getting the wind input right? And is it just because both models have the same wind input, they're roughly going to have the same front propagation, or do you really need to get the details of the kind of fuel and all the other stuff right to get the patterns right?
So that one, it isn't even that much more elaborate. The crazy thing about those models
is less efficient.
Is that they were using, so the validation against Farsight was really done to show the Forest Service this was just as good. And there's a lot of examples in physics where using like a cellular automata gives rise to rough boundaries, fractal boundaries in problems where it really should not. And that really has to do with the like the cellular automata like feature, the all or nothing. And so the advance of that was made with H-fire was to move to this raster based method, because a raster doesn't say I've just completely burned out my cell, I'm progressively burning it at a rate that depends on these parameters. And as a result, it produced a boundary that wasn't all weird and rough and fractal. And so, and yet it had the advantage of being local. So the way that the traditional model spread was it had these expanding ellipses that it integrated forward, and then it drew a new perimeter connecting their endpoints, and that couldn't get around bottlenecks. So that model would just stop, it would not be able to be, just couldn't simulate in a rough terrain. So I think that was where the advantage was to move to raster based models. And then what I would call really high fidelity are the ones that really try to put in true atmospheric conditions and combustion and things like that. And those are so slow you would just basically be able to watch fire spread along a strip and say, oh, it's able to generate these turbulent patterns, which is interesting. But it's not something you could ever do over the course of numerous, like decades of catalog type fires. It's more one at a time and just to isolate a phenomena. Yeah.
I was going to see if I could sneak in a conceptual question here. So, Jean, you mentioned a few times this notion of robust yet fragile trade-offs, and alluded to the waterbed theorem and waterbed effect, and which I guess is partly what inspired that idea. And so I know that this is a theorem of linear systems in the frequency domain, and that there are some generalizations that you can try to do in the time domain with information theory techniques. But it struck me that you were sort of using it maybe in a more general context, and I was trying to figure out, to what extent is that kind of metaphoric, and if so, since it seems to be kind of getting at something essential, is there sort of a more general theorem kind of lurking there about these trade-offs?
I think there is. I have I don't have, I don't think we've ever sort of sat down and proved it. You're right. It's a frequency domain control theorem. And here it's a little bit more like, okay, I put in a robustness mechanism, and now I'm fragile to my assumptions about the robustness mechanism. So that's necessarily going to be true. And whether it's going to be an exact, sort of balance, push down here, pop up there, or whether it's just that real warning that you don't get something for nothing. That any kind of constraint is going to, if you allocate over here, you're going to have a pop-up somewhere else. So we've used it in lots of other cases. We've used it for thinking about the immune system, lots of other areas. This shows up in sort of health and things like that.
Right. But I guess this is just sort of the pretty physics sort of thing, but to the extent that you can tie it into something, as sort of general limits in the way that,
we should. Yeah, I think it's a very good question. It's a very, very, very good question. Yeah. I think there's something there. I haven't sat down and tried to do it again, but I think we should be thinking that way. I think it's a really interesting way to think, especially as physics has become more about, the biology and the design materials, things like that. It comes up. I think it was a theme that we thought about a lot in that sort of hourglass motif across systems. And there are some systems where the design choices are extremely structured, yet there are other systems where it's harder to really think about, like, well, what's the design in an earthquake, or a mountain or something like that that's subject to avalanches. And yet there is a history of how these things are built that impacts their sensitivity structure in other dimensions. So, like, for instance, if you build a pile of grains, then shearing it in an opposite direction or something like that produces a response different from shearing something in the built direction. So I think there's interesting problems that could be looked at right along those lines across granular materials or other kinds of problems.
Yeah, that'd be pretty cool.
Network support type problem, like if you're in architecture, there's problems to think about in terms of how the built support structure creates, robustness to certain kinds of movements, but sensitivity in opposite directions. So we've looked at it, but we haven't quantified it as like a theorem, but it should be. There's something there, yeah.
Jean, I have a quick question, would be the last one. I don't know if anyone else has any questions. It's getting late, but if someone wants to work in an area like this, where do you start? What did you talk to? I think you mentioned you talked to the geography department and or how does it work?
Yeah, so for me, I think, it kind of grew out of thinking about complex systems and mechanisms for complexity. And I'd been doing earthquakes, but I also had done just basic stuff on looking at these sort of self-organized criticality models from a mathematical point of view. And then I was friends with John Doyle, and people were starting to talk about forest fire model. And so out comes this other work. And then we went and talked to the people locally who were working on this, and they were very receptive, really excited, actually.
We're academics or in the fire department?
In the fire, yeah. So we talked to people in our geography department who were developing these models, and we were looking at it in a way that was very out of the box for them. And I think, we've had the same kind of experience with earthquakes, where we kind of we talk to the people in this area that have some overlap with what we're doing. They're very receptive to a different idea, as long as you don't come in and say, I've solved all your problems,
Right.
I'm a physicist, if you go in and you talk to people and you listen to what their questions are, then very frequently you'll have a new approach. It's very welcomed. And that's been my experience over and over and over again in interdisciplinary work. It's just a question of talking to people, and often in my case it starts at my own university, and then it's a new way of thinking often, and you have to listen to their way of thinking too. But I think that there's so many areas now, and also there's so many calls for multidisciplinary approaches to these kinds of big problems, like wildfires right now is an area which is getting funded through the infrastructure bill. And I think that they're not asking to just fund the pyrogeographers. They're trying to find multidisciplinary teams that can come together. And so then what you'll find there's a lot of research that's been done in a siloed way. So you'll have your geographers, you'll have your social scientists, you'll have your engineers, and they have all done something, but they haven't necessarily integrated their projects. And so I think that's really a huge opportunity for people with physics, because you'll come into it with a systems thinking. And a lot of these problems are incredibly benefited by not necessarily just linking up the most advanced fire model with the most advanced transportation model. In order to really understand and isolate the trade-offs, you have to come up with a simple illustrated
model,
physics-like model that takes enough into account what their concerns are. And then that shows people where they should be looking. So I just, encourage you to drop into, your other departments and talk to the people,
Thank you. Thanks.
Yeah, and that's a really good point about talking to, but also being able to listen, and that's
we know how to talk.
For some physicists, that's
Listen.
important, so.
Yeah, and I think the listening is super important. And interestingly too, there's so much of like the networks approach really has been, evolved maybe first, but also in parallel in the social sciences. So a lot of the stuff that we've called our network stuff, that the growing network, social network, things like that, they've been thinking about a lot of that type of stuff for a long time. So you'll increasingly find that there are these interesting overlaps, and yet a physicist will bring a different approach. And I would also say, don't be wedded to random graphs, right? I mean, look at the topology of their problem, because putting in a little bit of the topology of the real problem is extremely important and can change the whole behavior, right? So that's the story of the critical phenomena versus the hot model, is it's not just like, I'm going to talk about random graphs. And that's been true in network science too, where some parts of that have sort of started off as very random graph, random graph, random graph. Nothing's a random graph. And if you put in some of these design choices and look at the trade-offs, you start to get behavior from things like communication networks that look a lot more like what the actual communication network bottlenecks wind up looking like.
Right.
Yeah. So that's another whole story, which I but, yeah.
Thank you, Jean. Well,
Okay.
I don't know if there are any other questions. I think it's almost 1:30, 10:30 for you.
Yeah. Well, thank you. I really appreciate it. I see one question about cloud seeding. Can that help create rain? So there aren't many clouds. I mean, there's a ton of smoke, but I think a lot of the fire issue is bigger than that. So it's something where, you know, we would love to see rain, but we're dealing a lot of times in situations where the humidity is very low. One of the interesting things that happens in Santa Barbara is the marine layer that comes in at the ocean during periods that are very dry. It actually helps protect some of the coastal region this year, is that you can have some high humidity regions, because fuel moisture is a big factor. And I think that we would love rain, but you know, we're really limited in terms of moisture when we're in the large, you know, fire season. Anyway, okay, I want to thank you all again for
Thank
your
you.
attention.
And thank you. Yeah.
Inviting
Thank you,
me.
Jean. This
Take
was
care.
wonderful. Thank
Yeah.
you.
Okay.
Take care. Bye.
Okay. Bye.
Bye.